Properties of Liquids, Gases, and Vapors, Part 1. Narrated by Susan Arnold. Animations provided by Derek Siebert. Understanding how chemical and physical properties influence a chemical's behavior is important for recognizing chemical hazards, and the ideal gas law provides important insights into these behaviors. In Part 1 of this module, we'll briefly review Boyle's, Gay-Lussac's, Raoult's, and Henry's laws. In Part 2, we'll relate some of these properties and behaviors to exposure routes and exposure potential. Let's start by defining what an ideal gas is. An ideal gas is a hypothetical gas in which the molecules move about randomly, where they're not influenced by intermolecular interactions. They move freely in all directions and are impacted only by collision and with other molecules, without any loss of kinetic energy. The ideal gas law reflects these conditions. In the ideal gas law shown here, P is the pressure of the gas, V is the volume taken up by the gas, T is the temperature of the gas, R is the gas constant, and N is the number of moles of the gas. The balloon in this image is intended to illustrate the relationship between the variable volume of a gas as it relates to temperature and pressure. As you will see, the laws that are subsequently reviewed express the relationships between these different variables under specific conditions. Boyle's law expresses the relationship between pressure and volume and demonstrates that for a given chemical mass, the pressure exerted by a gas is inversely proportional to the volume occupied by it, provided the temperature remains constant. As you can see in this animation, as the volume is reduced, the gas molecules collide more frequently with the walls of the container, exerting more force onto the walls and therefore increasing pressure. Chemicals that are stored in a compressed state will be under pressure that is greater than atmospheric pressure. If the storage container is opened or has a leak, the pressurized system will propel the chemical outward, displacing it at a rate that is much higher than ambient diffusion. It's important to account for this increased energy when designing engineering controls intended to capture or contain emissions of chemicals under pressure. Gay-Lussac's law expresses the relationship between pressure and temperature, with temperature expressed in Kelvin. It tells us that when the volume is constant, for example, the container with a constant volume shown in the animation, there is a proportional increase in pressure as the temperature of the gas is increased. Accounting for an increase in pressure when temperatures increase is an important process safety consideration. It's also an important factor when dealing with toxic chemical vapors, which we'll discuss in greater detail in Part 2 of this module. Charles's law describes the relationship between temperature and volume of an ideal gas. It's named after the French physicist who discovered this relationship, Jacques Charles. The formula indicates that when the temperature of the gas increases, with the pressure held constant, the volume of that gas will also increase. Vapor pressure is the pressure exerted by the gaseous phase of a two-phase system on the other phase, either a liquid or a solid. Molecules in the vapor phase collide with the walls and lid of the container, causing pressure. If a substance is in an enclosed space, the two-phase system will arrive at an equilibrium state after some period of time. At equilibrium, the evaporation rate equals the condensation rate. This equilibrium state is a dynamic, balanced condition with no net change of molecules between the two phases. That means that the rate at which the molecules evaporate to become vapor equals the rate at which the molecules condense to become liquid or solid. The evaporation and condensation occur at the boundary of these two phases. The time it takes for a system to reach equilibrium can be difficult to predict. At a given temperature, the pressure of the vapor measured at equilibrium state is the equilibrium or saturated vapor pressure. This pressure is a fraction of the total pressure associated with the specific chemical. Total pressure is equal to 760 millimeters of mercury at sea level. So if the temperature increases from its initial temperature, the vapor pressure also increases, resulting in an increase in the evaporation rate, which is demonstrated here by the increasing rate at which the bubbles form in the liquid and escape into the gaseous phase. This relationship was described earlier by the Gay-Lussac law, P1 over T1 equals P2 over T2. The vapor pressure of a chemical can be altered by its interaction with other constituents when it is part of a chemical mixture. Generally speaking, the vapor pressure of the chemical constituent tends to be lower compared to the vapor pressure of the pure chemical. When a chemical spill occurs that involves a chemical with a measurable vapor pressure, the vapors that have evaporated from the liquid can be released into the air above it, presenting an exposure risk to those near the spill. When enough energy is applied, such as when heat was applied in the animation shown earlier, and the liquid begins to boil, the vapor pressure becomes equal to the atmospheric pressure, 760 millimeters of mercury at sea level. Generally speaking, vapor pressure increases with increasing temperature, and approximately doubles with every 10 degrees. Vapor pressures and boiling points are usually reported on safety data sheets or are available in standard sources. For example, online sources such as PubChem or the Hazardous Substances Database or the NIEHS Pocket Guide. For comparison, vapor pressures must be reported at the same temperature. These are usually reported at ambient temperatures of 25 degrees C. This chemical relationship between boiling point and vapor pressure, and more broadly, temperature and pressure of a chemical in a two-phase system, are extremely useful for predicting chemical behavior. To understand vapor pressure in chemical mixtures, we must first define several technical terms. We define solute as the solid that is dissolved in a liquid to form a homogeneous solution, and the solvent is defined as the liquid into which the solid has dissolved. The solute is then said to be soluble in the solvent. When two substances with similar polarities exhibiting similar intermolecular interactions are combined, they're described as being miscible. Some examples of miscible solutions are gasoline, which is a mixture of several organic solvents, including benzene, toluene, xylene, and ethylbenzene. Another example is alcoholic drinks that contain alcohol and water. For chemical mixtures, the vapor pressure of a chemical component of that mixture changes with the solvent-solute interaction. The adage, like dissolves like, is relevant here. Chemical constituents of a mixture that are very similar with respect to their molecular structure and chemical properties will behave in a way that's more consistent with the ideal gas law. In these kinds of mixtures, the change in vapor pressure will track closely with the molar fraction of that chemical in the mixture. Raoult's law reflects the change in vapor pressure of a chemical component according to its mole fraction in a chemical mixture. For non-polar chemicals, such as organic solvents, that tend to behave as ideal mixtures, Raoult's law gives a pretty accurate estimate of the adjusted or partial pressure. Chemical constituents that constitute a large percentage of the total mole fraction in chemical mixtures containing constituents with similar chemical properties exhibit smaller changes in the vapor pressure. The partial or adjusted pressure in these cases tends to match empirically measured pressures. As the mole fraction decreases, or the similarity in chemical properties across the constituents in the mixture lessens, changing the nature of the intermolecular interactions within the mixture will deviate from ideal behavior. The intermolecular interactions can be accounted for by using an activity coefficient, which is denoted by the Greek symbol gamma. In some cases, other laws and equations may be more appropriate for predicting the adjusted vapor pressure. Henry's law expresses the adjusted vapor pressure based on the dissolution of the solute, which is surrounded by a liquid solvent. According to Henry's law, the amount of solute, denoted here as component A, is directly proportional to the pressure it exerts when it is at equilibrium with the liquid and is called the partial pressure, and sometimes referred to as the adjusted pressure. The proportionality constant denoted here as K subscript HA, is called the Henry's law constant. We can use this relationship expressed in this equation to estimate the partial pressure or adjusted pressure of the component. Henry's law states that the vapor pressure of the solute in the mixture is reduced by Henry's law constant times the solute, component A's molar concentration. Henry's law constants can be found in reference texts, such as the CRC Handbook of Chemistry and Physics, and online from sources such as the National Library of Medicine's PubChem. Let's consider two examples to explore the concept of partial or adjusted vapor pressure. You don't need to memorize the list of chemicals or the values that you'll see. It's the relationships that are important here. In this first example, two organic solvents, toluene and ethyl acetate, are combined in a mixture. As you can see in the column on the right, labeled WT, each chemical represents a different weight percent of the total mixture. This information is used to determine the mole fraction each chemical represents by dividing the weight percent by the chemical's corresponding molecular weight, which are not shown in this table. The vapor pressures of the pure chemical for each component are shown here in the last column on the right. The adjusted vapor pressure, or partial pressure, of the chemical in the mixture is adjusted using the mole fraction of each constituent and the vapor pressure of the pure chemical by applying Raoult's law. Notice that the adjusted vapor pressures, or partial pressures, are about 1/2 of the pure vapor pressure values. This is not surprising since each component represents 50% of the mixture. When the mixture involved includes polar compounds, or when the mixture involves a very dilute solution, the mixture may behave in a way that departs from the ideal gas laws. In these cases, the application of Henry's law will likely produce a more accurate estimation of the vapor pressure. Consider this second example. Methanol is miscible in water. Like water, it's a covalent polar molecule. Acetone, on the other hand, is essentially nonpolar. For this mixture, Henry's law is preferable for predicting the adjusted vapor pressure. In addition to the mole fraction for each chemical, Henry's law constant is needed to apply Henry's law. These can be found online or in lookup tables from tools such as the SDM 2.0 or in reference texts such as the CRC Handbook of Chemistry and Physics. The adjusted vapor pressure is then predicted using Henry's law constant and the mole fraction for each constituent. For comparison, these tables show the same mixture that was used in example 2, showing the adjusted vapor pressure values based on Henry's law in the first table and Raoult's law in the second table. Remember that this is a dilute aqueous mixture with some interactions between the two solute constituents. As you can see, the predicted vapor pressures using Raoult's law are much lower than those predicted using Henry's law. Predicting airborne concentrations of chemical vapors resulting from their evaporation from liquid surfaces of chemical mixtures is highly dependent on accurately predicting their partial or adjusted vapor pressures. Thus, evaluating the chemical properties and selecting the appropriate equation to predict the adjusted vapor pressure is very important. This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.